Swayam Prabha. Digital India. Educated India.
Welcome back to the lecture number 4 of this week. Last lecture we stopped at differential manometers. This was the slide that we were going to talk about. We saw some devices that can be used to measure pressures. One of them was manometers, in which a standard manometer and a differential manometer. So we are actually going to write down an equation, or you can call it as a numerical as well. So this is the setup, the blue one is this liquid here is water, and this is mercury. So we need to find out the drop in pressure between points 1 and 2. Okay. So how are we going to approach this problem? So where, if you see, this is an orifice, correct? So now we are actually going to keep this figure in a small and just start writing down the equations, variation with pressure. If we go down, we are going to add the pressure. If we are going up, we are going to subtract that pressure. So firstly, P1, this is P1 here, plus H1 gamma W. So what we are traversing around this direction, okay, H1 gamma W, because this is water, minus H2. So if we traverse around this direction and reach this point, okay, so minus H2 into gamma Hg. Again we are traversing across the water, so minus H3 gamma W should be equal to P2. Very simple equation, correct? So we can bring P1 here, P2 here, and we can write P1 minus P2 is equal to, as written here, right, H3 minus H1 gamma W plus H2 gamma Hg. Or we can also write P1 minus P2, H3 minus H1 is what? If you see, H3 minus H1 or minus of H1 minus H3 will be H2, right? So this can be written as minus H2, this term here. So it will be, H2 can be taken out and we can write P1 minus P2 is equal to H2 gamma Hg minus gamma water, and this is the pressure difference. Very simple question on differential manometers, and this is how it works. Okay, nice. So this concludes my first part, where the pressure variation with location was there, pressure at a point. So we are going to solve some questions also, and this is quite important. So what we say, we have a 6 meter deep tank. So this is 6 meter, right, and contains 4 meters of water. So this is as it is written here, very clear, 4 meter, and 2 meter of oil of relative density 0.88. So we have an oil, the relative density is 0.88. We have to determine the pressure at the bottom of the tank. Okay, so for your convenience, we have drawn the pressure variation here on this side. Okay, this. Okay, so how are we going to, this is a question that generally people do it for before engineering starts, or you must also have done it in your fluid mechanics class. So now we are going to approach this, and as always what I am going to do is I am going to use a white screen. So we have already seen this equation, so I will just draw the pressure prism. should not call it pressure prism, but yes. So this is P2, right, the entire thing here. This is 2 meters, okay, so that you remember pressure at atmospheric is 0. This is 4 meters, okay, and if this is P3, we need to find this, correct. So these are all the information that we have. So first, see, steps are very important, so you must be noting it down. First, determine the pressure while water interface, right, that is P2. So P2 is written as P1 plus pressure due to 2 meter of oil. Very nice. So or P1 plus what is the pressure due to 2 meters of oil? Gamma naught into 2, correct. Here P1 is equal to 0, right, whereas gamma naught, which is the pressure of the oil, it's 0.88 specific gravity into 9790, that is 8615.2 Newton per meter square, no, Newton per meter cube, sorry, because this, yeah. So P2 can be written as 8615.2 into 2, that gives us 17230.4 Newton per meter square. So you don't have to be very specific about 9790, you can also assume 9.8, so 9800, it's just what I have assumed, okay. So that is the first step. Now we must also determine P3, right. Gamma W is, we have assumed 9790 Newton per meter cube, okay, yeah. So P3 will be P2 plus pressure due to 4 meters of water, right. So P2 we already know, correct. So P2 value, P2 is what we have found out was 17230.4 plus pressure due to 4 meters of water is going to be 4 into 9790, okay, that gives us 56390.4 Newton per meter square, or P3 can be written as 56.39 kilopascal, okay. So this was what the question had asked, to calculate P2 and P3. If we just go back, if we, so determine the pressure at the bottom of the tank. So bottom of the tank was P3, and that is exactly what we have found out. So the answer was P3 is equal to 56.39 kilopascal, okay. So maybe all right. So I have another problem for you before we go to the next concept, and that is, we have shown a manometer here in this figure. We have to calculate the pressure difference between points M and N. This is point M and this is point N. The best way, as I told you before, if you want to calculate the pressure difference or pressure at that point, you have to start at one point where the pressure is known and traverse to the other point where you have to calculate the pressure. If you go up, you have to subtract that pressure. If you go down, you have to add that pressure. So that is the one of the ways. Here what we are going to do, we are going to equate the pressure at this level. Okay, so I think you must be drawing this figure, because I won't be redrawing it now. So but what I am going to do is I am going to use that another white sheet to be able to solve this problem. Good. So as I already told you, we have to equate. So equating the pressures at both the limbs, as I told you while discussing the figure, along the horizontal plane. And what is that plane? XX. Okay, so PM minus gamma W 0.06 plus 0.035 will give us Pn minus gamma W 0.12 plus 0.06 minus gamma naught into 0.035. So here gamma W is unit weight of water, which is equal to 9790 Newton per meter cube, and this value has been assumed. Okay, this is a standard value. What is gamma naught? Is unit weight of oil. What is it going to be? Any guesses? The specific density was 0.83 into 9790. Specific gravity, when we say, it's always a density that is in ratio with water, no other fluid. Okay, so that is why the density of, unit weight of water is what we multiply to the specific gravity to get the unit weight of that oil. So here it comes out to be 8125.7 Newton per meter cube. So if we use these two values in equation here, what we are going to get? Pm minus Pn is equal to 9790 into 0.095 minus 9790 into 0.18 minus 8125.7 into 0.035, and this is going to give us minus 1116.5 Newton per meter square, or minus 1.1165 kilopascal. We don't have to be very, where we can simply write 1.12 also, minus 1.12 kilopascal. Okay, so the answer is going to be, because it's negative, that means pressure at N is larger than at M by 1.12 kilopascal. Simple. So the calculation of the pressure things is not that difficult. If you follow the chain rule, keep writing the pressure while going up and down, this is very, very, very simple. Great. So now we go back, and this we have solved this problem now. So, this is fluid statics 2. I mean, I call it 2 because we are going to do the surface forces and body forces. Therefore, we need to know what are we going to study in fluid statics 2. So, in statics 2, it's static surface forces. We are going to see force on plane areas. Okay. We are going to see force on curved surfaces like this. So, this is plane areas, this is plane, this is curved surface, and we also will see the buoyant force, a very small detail of it, but I think this is very necessary. So, I mean, if we are teaching basics of fluid mechanics in this course in the beginning, so buoyancy is an important concept that everybody must be aware of. Good. So, we have to see what are the forces on plane areas, that is horizontal surface. So, if you see, this is a figure that shows, you know, a horizontal surface at depth h. Okay. So, this h is the vertical distance to free surface, and this what is the p here, okay, and what is the resultant force at the bottom, okay. And P we are assuming 500 kilopascals here, okay, that we are going to see. So, what is the force on the bottom of this tank of water? Actually, what is the net force on the bottom of this tank? So, the force, resultant force is going to be the integration of pressure into area. So, P is constant, so it comes out and that becomes pressure into area, PA, where P is rho GH, okay. This is the gauge pressure. So, Fr will become rho GH into A. HA is the volume, area into height, that is the volume, right. So, Fr is actually nothing but the weight of the overlying fluid, okay. Also, F is normal to the surface and towards the surface if P is positive, okay. F passes through the centroid of the area. This is an important information for you. And therefore, the change in pressure can be equated to rho into A, okay, or we can write in x direction minus delta P by delta x is equal to rho Ax, right. So, there is no acceleration in x direction here, and that is equal to 0. There is no pressure variation in x direction, whatever there is, it is in z direction. Good. Another important thing is we have to learn or revise again what are the forces on the plane areas or the inclined surface. So, this has to be taken in a little bit of more detail. What will be the direction of the force? Always perpendicular, normal to the plane, right. So, the force will start acting like this, correct. What will be the magnitude of the force? We have to integrate the pressure over the entire area. Here the pressure is no longer constant at the, because it's not at one elevation, it's varying. See, the H is changing here, here it's different, here it's different, here it's different. So, yeah. What is the line of the action? So, to find the line of action, we have to do the moment of the resultant force must be equal to the moment of the distributed pressure force. We have to do the moment balance to find the line of action. We will see soon how are we going to tackle that. So, I will just erase all ink on this slide. Good. So, forces on plane areas. So, this has been taken actually from Monsoon, Young and Okishi, the derivation. So, but I think I will explain one by one what those things are. So the biggest question is, we have to determine the location, direction and magnitude of the resultant force acting on one side of this area due to the liquid in contact with water. If you see the body, okay, I will just erase because this was just to okay, all right. What we say, let the plane in which the surface lies intersect the free surface. So, this is the free surface here, okay, and let the plane in which the surface lies, the body, intersect at point O, okay, right, good, and let this make an angle theta with the surface, right. The xy coordinate system is defined such that O is the origin. So, this is also the origin, and the x axis is directed along the surface as shown. So, this is x axis, okay, sorry, this is x axis and this is y axis, good. So, this is just explaining you, and we are going to look at the individual terms when we describe those. You see many things here, centroid, location of resultant forces, you see this FR, you see DF, but we will come to it one by one, good. So, what I have done is I have kept this image on the left side, and now we are going to, so for any depth h, okay, let we say that the force acting on an area dA will be, because it is at depth h, dF will be pressure into area, right, gamma h dA. This is the dF, this is perpendicular to the surface, that is very important. So, to find out the resultant force, what should we do? We do gamma h dA integrated over the entire area, right. H here, if we try to write it down in terms of y, this can be related to theta as h is y sin theta and gamma is gamma and dA is dA, okay. So, Fr can be written as gamma sin theta can come out, and this is y dA, okay, integral of y dA. Very important, if you remember from your earlier classes, this is first moment of inertia, and this integral y dA can be written as yc into A, where yc is the location of the centroid of the object, right, and Fr can be written as gamma A yc sin theta. So, now you know gamma, you know A, you know sin theta, and for a particular object you also know yc, the centroid location, right, where yc is the coordinate of the centroid of the area A measured from x axis which passes through O. So, orientation you have to be very careful about, okay. I will just erase all the ink now. So, or we can also say gamma A from here and yc sin theta. What is yc sin theta? This is yc, right? Yc sin theta can be written as hc. Hc is the height of the centroid from the free surface. So, hc is the vertical distance from fluid surface to the centroid of the area. Now, we have actually simplified into very common, very simple equation. I will erase, so I will just write the important one. So, this is the important one, Fr is equal to gamma AHC. This is one important result to note down at this point in time. Very good. So, we proceed to the next slide. Okay. So, this equation of Fr suggests that the magnitude of the resultant force is equal to the pressure at the centroid multiplied by total area, as you have seen here. See, pressure gamma A multiplied by the total area, right. Fr also must be perpendicular to the surface, that is very important, and the reason is since all the differential forces were perpendicular that we have counted. If you see all the forces, these were all perpendicular. So, this is, let us say, df1, df2, df3. So, if you add this, the sum can change, but not the direction, right. The point through which the resultant force acts is called the center of pressure. This is, you might have heard in your fluid mechanics class what calculate the center of pressure. So, this is what the center of pressure is, a quick revision for you again. The center of pressure is not at the centroid, and what is the reason? Because the pressure is increasing with depth. That is important, again another important result to note down. Okay. We have seen the resultant force value and we have discussed some of the properties of resultant force. Now, we must also be able to find out what corresponding XR and YR is. So, let us say there is the one of the coordinates in y direction for the center of pressure. Centroid is here, this is center of pressure, right, is YR, which is not equal to YC. Good. Okay. In that particular case, what we are going to do is coordinate YR can be determined by summation of moment around x axis. So, for finding YR, the moment equilibrium should be done around x axis. So, the way we do it, YR FR. So, see YR into FR. So, this is YR into FR. This will be equal to integral y df, right. So, what is y df? So, this is df and this is y. So, all the summation beginning from here until here, all the small df's that is there. So, that will be y can be written as df can be written as gamma sin theta y dA, correct. This we have already seen in the previous slide. This is the sum of the moment, where Fr was gamma A yc sin theta, that we have seen before. So, YR now can be written as integral y squared dA divided by yc into A. I will erase the ink. So, you can see integral y squared dA, okay, divided by yc into A, because gamma sin theta cancels, right. So, this is actually the second moment of inertia with respect to the x axis. Very good. So, we are coming at some conclusions now, where YR can be written as Ix, second moment of inertia, correct. Now, if we use the parallel axis theorem, so because see this is around an x axis which is not fully independent of the coordinate center, right, system, but if we have a coordinate system passing through the centroid of the object, then we are able to calculate very easily, does not matter how do we orient our coordinate system. So, using parallel axis theorem, Ix can be written as Ixc plus Ayc square, very simple, that this you have read before as well. So, Ixc is the second moment of inertia with respect to an axis passing through the centroid and parallel to x axis. Therefore, the equation of YR can be written as Yc is the centroid plus Ixc divided by Yc into A. Ixc is known, Yc is known and A is known, right. So, this is an important so this is the important equation again. So, YR is Yc plus Ixc divided by Yc into A. If you remember this equation, you will always be able to find out the the center of pressure coordinate YR. So, we also need to find out XR. What is the logical way? We will do the summation of moment around y axis now. So, for XR we need to do the moment calculation around y axis. So, around this axis. How? See, XR into FR. Where is XR? This is XR. So XR into FR, okay, because yeah, is equal to integral x df. So df we already know, so it's gamma sine theta y dA, right? And this is sum of the moment. We know Fr is this one, gamma a yc sine theta. Therefore xr will come out to be integral x y dA divided by yc a, and this is the product of inertia I x y with respect to the x and y axis. Therefore xr can be written as I x y divided by yc into a. Again the same thing happens, that we need to translate this moment of inertia or product of inertia I x y with respect to the centroid, so that it becomes independent of that particular coordinate system. So we can write, if this is I x y, okay, and I x y c can be written as I x y is equal to I x y at centroid plus a y c x c. If we put this in this equation, here I x y c is the product of inertia with respect to an orthogonal coordinate system passing through the centroid, and therefore xr can be written as xc plus I x y c divided by yc into a. So this is xc here, what it comes. So so this is an important result here. This is good. Another important result, for we have obtained yr and xr. Now the center of pressure sum. If the submerged area is symmetrical with respect to axis passing through centroid and parallel to either x or y axis, the resultant force must pass along the x is equal to xc, since I x y is identically 0. See, if the submerged area is symmetrical with respect to axis passing through the centroid, then I x y is identically 0, so xr will be 0. Now as the yc increases, the center of the y coordinate of the centroid increases, center of pressure moves closer to the centroid of the area. Very it's easy to see from the equation that y r was yc plus, you know. So if yc is too large, then doesn't matter what the other term is. Since yc is equal to hc by sine theta, yc will increase if depth of submergence hc increases, or for a given depth the area is rotated such that an angle theta decreases. This is very obvious from this particular equation. So now there are some properties of area which you will be supplied with. This is very easy to, you know, hand on, you don't need to remember some other with this slide if you had. So area in this particular rectangle, area is AB, depth of the centroid is A by 2, Ixc is BA cube by 12. So this is symmetric about the centroid, right? So Ixyc is 0, where Ixc by A is A square by 12. I mean you can just simply see. Similarly for this triangle, isosceles triangle, this is for circle. I think you can, you know, note it down. These figures are quite important. The circle, for example, even objects like this, because in in hydraulics you will encounter structures like this having this type of gate. Ellipse is also important. So area is pi AB, yc is A, Ixc is pi b A cube by 4, Ixyc is 0 because it is also symmetric around the centroid. Similarly this here, so this the yc is 4r by 3 pi. This value is important because we are going to use it, because the most of the gates that are used in hydraulics have these type of openings. We will come and we will see in this type of, you know, thing. So this is the probably the last of this lecture. I would want to each and every one of you, this is a very basic question which I have taken from an English author. Location of average pressure versus line of action. So we will see in practice how this moment and those things are calculated with the help of these blocks. This is quite easy to understand. So my question is, what is the average depth of the blocks? Anyone? Tell me, what is the average depth? So this is 1, 2, 3, 4, 5. So what is the average depth? 3, right? Where does this average occur? Tell me, where is this average occurring? The depth, tell me. So it's happening at, see, at 5. Are you able to get this? Right? See, this is correct. See, the most number of the block number 3 is at 5, you know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if you take the depth. Now the most important, where is the resultant actually? How are you able to find this resultant? We will use moment balance here. So correct. So what we are going to do? We are going to do YR into FR. Resultant force is equal to 1 meter. So this is 1 meter. How many blocks are there? Tell me. 4 blocks plus, see, 1, 2, 3, 4. Okay. Now 8 blocks into 3 meters, right? 1, 2, 3, 4, 5, 6, 7, 8 into 3 meters. Now we have 12 blocks, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 blocks, that one. Similarly, we have 16 blocks, we have 20 blocks. And if we do this summation, so YR FR is equal to 380 meter blocks. Okay. And therefore 380 meter blocks, and the total number of blocks is 60 blocks. So we divide and we see YR will be 6.33 meters. So this is quite an intriguing example where you can practice it on your own, and if you don't understand, we will explain that in the forum. If you please raise your questions there. That's good. So now I will end this particular lecture and we will proceed to the last lecture of our this week, which is continuation of fluid statics, where we will see some more examples and how the forces on the surfaces is calculated more. Great. See you.